Our next speaker is Mahjouri-Samani from NanoPrintek, and he will tell us more about the dry multimaterial printing technology.
Thank you very much for the introduction, and thank you all for staying awake. I have difficulties staying awake myself, so thank you. So today I'm going to talk about dry multimaterial printing technologies. I know that you are mostly familiar with all the ink-based technologies that you've been seeing today and during past 15, 20 years. So I'm going to show you a new technology that does not use ink at all, and it is capable of printing pure multimaterial, multifunctional, and hybrid materials on demand. All right, just to pay the tax, we have to show this slide. You know, printed electronics is quite interesting, useful. One of the reasons is that we are moving toward Internet of Things, and we want everything to be smart. And every object will eventually collect data, will process data, and will communicate data with other objects in the network. So for this reason, we need technologies that are capable of printing various materials and devices onto the objects, well beyond silver. I mean, 90% of the talks that we see until today, during past many years, is all about silver and silver and silver. Now, printing functional devices requires, antennas, sensors, displays, batteries, capacitors, and so on and so forth. But how are you going to do this? We need technologies that is capable of printing metals, semiconductors, maybe insulators, composites, nanocomposites, alloys. How are we going to do those? Now, looking at the technologies that we have today, they are all ink-based. Almost all of them are using ink. For example, inkjet printing, aerosol jet printing. You can see that you need a complex and unsustainable supply chain for this ecosystem to work. For example, to make even one ink, it takes between 6 months to 2 years to formulate the ink. See how complex that is. And it's very expensive. Because of that complexity, it's very expensive, and it is pollutive to formulate the right ink with the right viscosity for the right machine. And the limited shelf life is also not so friendly with the environment and also costly. And the shelf life usually is about few months to maybe maximum 6 months. And if you forget to put your ink in fridge, you got to throw it away. And of course, you need to, after printing, you need to do a post-processing. This post-processing itself means money and cost. And it's very challenging. Some of the post-processing is not even compatible with the substrate that you're using. And eventually, machine cleaning and maintenance. Every single time that you use an inkjet or aerosol jet, you have to almost wash 50 pieces. If you don't do it, then you have to spend tons of money to replace that part. Now, above all, when you're talking about electronics, you do not want any single contamination in your system, right? Looking at the conventional electronics in clean rooms, there is a clean room. The reason is that you don't want any contamination in your electronics. And when you talk about ink, ink is all about contamination, right? You manufacture the ink, you print it out, and then you are suffering to remove all those contaminations. Now, with silver, maybe you're okay. Maybe you're okay with copper, but when you go to semiconductor, nanocomposites, composites, alloys, then that contamination is going to kill your entire device, okay? So that's basically the idea that we started thinking about the next generation of technologies that do not use ink. So this is putting into perspective how complex the ink-based industry is. You need to manufacture nanopowder. It goes to ink manufacturing industry. It goes to printing industry. It goes to post-sintering, machines and industry, and then finally you have the printed electronics. Now, we have invented a technology that integrates all those 4 industries into one machine. The way this machine works is you have a solid targets. Let's say you want to print gold. You take your gold out of your finger, you put it inside the machine, and the laser will generate nanoparticles in real time and on demand, okay? So you generate nanoparticles of 100% pure. Those nanoparticles will come out of jet, and then there is another laser that will sinter it in real time. There is no post-processing involved. So everything is on demand, pure. You can do multi-material, and then you can do sintering in real time. That's it. Now, as you can see, this is summarizing. No need for ink, no post-processing, no contamination. It is extremely eco-friendly. I'll give you, some example later on. You can do multi-material. If you have a carousel inside your print head, you can add as many targets that you want. And eventually, it is extremely cost-effective. For example, right now, if you buy a 100 milliliter of silver, it's going to cost you $500. Now, if you need a new ink, let's say zinc oxide or some complex BTO, tin oxide, it's going to cost you probably between 5 to 10K for a small bottle, right? And then, if you can print it, if you can make it, you can make it clean, then it's going to cost you a huge amount of money. But in this system, all you need is a solid target, which is going to cost you probably $500, and you can print it almost for months and maybe a year. So it's very, very cost effective in terms of the material use. These are some examples of the nanoparticles that this machine generates in real time. For example, this one is titanium dioxide, ITO, BTO, silver, copper, and so on and so forth. And then these nanoparticles are ranging between 3 nanometers to 25 nanometers. The average diameter is about 10, 15 nanometers only. And they are 100% pure. Now, if you create a jet out of those nanoparticles, you can deposit these nanoparticles on your surface. And if you have your printing system with CNC integrated, then you can print beautiful lines with high uniformity, with high purity, just like this. This is, for example, just before I come here, I printed these. This is about 50 micron through a 50 micron nozzle. All right? And then, of course, this one is unsintered, and if you sinter it, then it becomes beautiful sinter lined, of course. Now, with this system, we are capable of printing, well, similar to many of you, silver, as you can see here. And I don't know if I can play this. There you go. There you go. That's just for fun. Very nice and functional devices. Now, this one is a real-time video of printing silver on top of a Bayolex. This is a Bayolex substrate. Burns at 100 degrees C, basically. It's a stretchable, low-temperature substrate. And everything is happening in real time. You can see that's the real speed. Okay. And of course, just to show that this technology is reliable, we do a lot of measurements and property investigation. For example, we study the thickness variation, as a number of pass number or the printed layers. This is the layer by layer process. You can print even one layer, which is going to give you about 100 nanometer, or you can repeat it, go up to a few microns as you wish. And then we also study the resistance. Resistivity goes down to 10 to the minus 7 without optimization. And we have not done any optimization yet, and we are already reaching 10 to the minus 7, which is quite impressive. We do, of course, bending test up to, in this example, up to 100,000 cycle. We also do up to a few million cycle, and nothing. We don't see significant changes in the resistivity of these lines that we print. Of course, adhesion is another very important parameter that we want to understand. We do ASTM standard adhesion test on these, and you can see that we are getting 5B, which is the best adhesion you can get. We do also the lifetime study to see over time how it performs. This is up to a month. We have also done up to a year for both silver, copper, and other materials. This is just an example. Of course, for the soldering and reflow, if you have good adhesion, then you do not have the balling effect on the surface. That this shows you that. And reliability test over million cycle. You can see that it is holding together quite nicely without using any glue or epoxy on the surface. Okay, this one is an example for copper. Again, same principle. You put a solid copper target inside the machine. Everything happens in real time. Nanoparticles are generated, coming to the surface, and laser is sintering in real time, and you get this beautiful copper printed, just like a fresh penny. And this circuit has been working for 1 year, and it still works. So, So beyond silver and copper and metals, you want to have multi-material printing and maybe printing multifunctional materials. So here is an example of printing silver, and then in between these cross lines, we printed aluminum oxide, and then continued the silver line on top of this, and you can create this bridge. Same thing here. You have silver line, aluminum oxide in between. We can print side by side, silver, tin oxide, zinc oxide. Same thing here, BTO, tin oxide, titanium dioxide, or we can print on top of each other and create stacked layers as you wish. Okay, of course, when you're printing composites, ceramics, and semiconductors, you want to make sure that your printed materials are pure and they have good quality. We do some study, Raman study up here. We also do XRD, and then you can see from here that they are extremely, extremely showing that you have good qualities of print. In this example, for example, BTO, TiO2, tin oxide, zinc oxide, and we have many others. Okay, another area that we are also targeting with this technology is printed electronics on papers or papertronics. These papers are different than papers that are being used for ink. In ink-based papers, they are either laminated or waxed to make sure that your ink liquid is not soaking the substrate. And these papers that we use, they are biodegradable and water soluble. We first study the threshold of laser burning of those papers. Once we find the optimum windows right here, then we go ahead and we print our, for example, here silver line on paper. This is a cross section of the print. And then we do some study, pass number versus thickness and so on and so forth, and resistivity. We get 10 to the minus 7 on paper. Again, the reason that the quality is quite interesting is, again, we don't have any contamination, any coating, any liquid, any additives in the system. It's pure nanoparticles. And then this is an example of a circuit board on paper. And this is just a video showing you that we are printing on paper without burning the paper. Okay? This is showing you, of course, the paper burns without leaving any residue. And then the second one is showing you that the paper dissolves in 20 seconds. So if you're printing transient electronics for whatever application, this is a great way of doing it, printing on this, and then it will dissolve after the function is done. Now, this is quite important. The reason is that as we are moving forward, let's say printed electronics someday is going to take over the world, then you are going to end up having billions and trillions of tons of polyamides and polymers and plastics of your substrates. How are you going to deal with those? Well, if you have technologies that can print on paper with different density and different lifetime, then you can basically contribute to that pollution problem. Of course, we can also print 2D and 2.5D and 3D. This one is showing you the white line that you see in the print. They are sintered silver in this example. The black lines, they are unsintered. So basically, we can do selective sintering during the print. And eventually, when you can, I don't want to take much time here, but well, I cannot move it forward. But this is going to be Einstein's figure at the end, 2 layers of print. And this is the technology that we have. The machine is built, ready for customers. And then here is the software. This is the smart manufacturing interface software that it does everything. You put your Gerber file or you draw your circuits on the machine, and the machine starts generating nanoparticles right there, and then there you go. It's following the lines, printing in real time. That's the real-time print. And there you go. And that's how it works. Now, if you want to change, this machine has 6 targets inside. So you can program it to print material number 1, and then go to number 2, and then go back to 1, go to 3. In whatever design that you have, you can basically program this machine to print it for you. All right, so just to summarize the technology, you can see that in this technology, you don't need any ink, or it does not use any liquid in the system, so no contamination. All you need is a solid target. Because of that, you have very easy transportation. Shelf life is the shelf life of the target that you have, maybe thousands of years. And then you have, of course, you can do on-demand and in-situ formation of dry and pure nanoparticles, real-time sintering and integration, no post-treatment treatment processes, environmentally friendly process, hybrid, multimaterial, and composite printing, and of course, it is suitable for printing on printing in electronics, sensor, microbatteries, supercapacitors, catalysts, and so on and so forth. And of course, you can also do simultaneous subtractive and additive as well, because it's all laser process. And with that, I would like to thank you for your attention. Thank you so much.